So, in the last class, we had discussed about all these DNL problems, or basically, we had a discussion about errors, and we have broadly classified the errors as static errors as well as dynamic errors. And we were looking at under static errors that there are four different types, and one can categorize those errors as linear errors and non-linear errors. And we have already spoken about the two type of linear errors, which are offset error as well as the gain error, and we had a glimpse of this differential nonlinear error as well. Okay. Now, let me just quickly jump on to what we have discussed. We had a discussion about this DNL, or basically differential nonlinearity, and we said that for a DAC, with respect to a DAC, a DNL is measured as something like actual height minus the ideal step height. Okay. So, the word height basically comes just because for a DAC, the y axis basically defines the voltage values. Okay. So, this is one of the specific reason why we have uh, this measurement of height when we speak about a DAC architecture. Okay. So, probably when we discuss about the ADC architecture, you will be clear in defining the DNL for an ADC, but as of now for a DAC, any error in general is measured with respect to some sort of voltage signal or some sort of signal which is analog. Okay. Yeah. So, later we just spoke about how to measure a height. So, because we are measuring a height, there is no existence of DNL of 0 in any of the cases. Okay. So, we begin with DNL of 1, where we look at the decimal equivalent value of this 001 and then check for the point. Okay. So, maybe, yeah. So, check for this particular point and try to measure the height by measuring from its previous value. Okay. So, the previous dot that we had when we had a value of 000, we had an output that is equal to 0. Okay. So, from that value to the current value that we are taking as DNL of 1 is red. Okay. So, that height is basically 1 by 8, and that is taken as the actual height, and that has to be subtracted by an ideal step height. So, the ideal step height is nothing but is the one that defines or defined by this VLSB, uh, which is nothing but V reference divided by 2 to the power n, which is an important quantity, or one can also be defined, or this can also be defined in terms of normalized quantity as just LSB, and that is defined as 1 upon 2 to the power n. Okay. So, in that case, when the value of n is equal to 3, this becomes 1 by 8. Okay. So, and later we just try to identify the renal of 2 by reading out the value uh, of digital data 2, try to find the point and measure the height from the previous point. Okay. So, from this point we have to measure, that is from 001 point, we have to measure the point of uh, 010, and that gives us the actual height minus the ideal step height, which is always an LSB value. Okay. So, this is how we did all this computation, and I guess after this we had also a discussion about this quantities, right. Yeah. So, now let me just begin looking into a DNL for, sorry guys, I've not opened the pictures, just a second. Yeah. Yeah, and also one can also plot this DNL as a kind of graph, the errors as a kind of graph. I'll just quickly do that, and it's basically, the graph is, So, I think in this particular question it is not asked, so we will just skip that. Yeah. So, now with respect to ADC, let me try to define the DNL. Okay. Now, with respect to ADC, the DNL will be a little bit different. Okay. So, which means that we have to think about the uh, statistic, or basically the transfer characteristic of this particular ADC. We know that for an ADC, the input is basically or basically the x-axis is nothing but your input, which is in terms of analog signal. So, that would be normalized as V in with reference to V reference. Okay. And the y-axis would be your digital output. So, this would be your digital signal D. Yeah. So, now in this case you would find that all the analog signals are basically defined with respect to the x axis, clear. So, in a way when we discussed about the DNL for a DAC, we had a DAC architecture having the transfer function where we had something like V out on the y axis, and due to which we had a DNL definition as something like step height, actual step height uh, minus the ideal step height, just because the voltage term was referred with respect to the y axis and we were trying to measure the differences between them. So, in this case what happens is that the analog signal is being mapped onto the x axis rather than a y axis in the previous case, right. So, in the case of an ADC, it maps onto the x axis, and due to which we also have discussed about the step response, which is an offset, not exactly step response, but what I said was for a 3-bit ADC we had we are trying to map a range of signals to a single value, and we had discussed about what is known as quantization error. And in order to make sure that all the errors that we have in our data converters, it has to fall within this plus or minus LSB. What we did is that we just shifted the entire graph by half LSB towards the left, okay, and due to which any value or any voltage value that falls within the range of 0 to a, a value which is equal to 1 by 16 were being mapped onto a single digital data, okay. So, now because of this entire signal range is being mapped onto a single data of 000, it introduces some sort of quantization error, and we had all those discussion in the last previous class, okay. So, let me not explain too much about it, but uh, the kind of graph that I would get is something like this, right, like a kind of step kind of graph is what we would end up having it, okay. Yeah. So, now in that case one could measure the value of DNL as the actual step width, okay. So, in this case it is defined as a step width just because the y axis, sorry, the x axis is basically defines our analog signal, and due to which it is the width that we will be measuring for the measurement of DNL, okay. Yeah, minus the ideal step width, okay. So, with this definition let us quickly just try to get a picture that will evaluate the DNL error of this following graph. Okay. So, I am just trying to paste the transfer function of the, yeah. So, this is the transfer function that we have, and let us try to evaluate the DNL error, okay. Yeah. So, now again, as I said, the DNL error is basically measured right from the value of 1, okay. So, it is never measured from the value of 0, and here in this case these errors, DNL error or the further down the INL error, those are the errors that will be read only after removing the offset error as well as the gain error, okay. So, it is something like a sequence. So, whenever you want to measure a DNL error, one has to ensure that you have read the offset error, remove that offset error from the transfer function, and then you go for a gain error, and again remove those gain errors, and then when you want to evaluate the DNL, ensure that both these errors are being removed from the transfer function, and then you try to evaluate it. Okay, so with that, again the DNL of 0 will never exist even in the case of a ADC. Okay, so hope that I am not confusing you people, but in short the DNL always begin with a value of 1. Okay, either it is a DAC or an ADC. So in this case, how will I measure the width of this particular step width? Okay, so in that case, I have to look for this value of 001 and then measure its width. Okay, so now clearly you could see that the width is falling across these two extremes. Okay, and the width of this one is basically measured as 1 by 16 minus 3 by 16. I guess it is right. Let me just work it out in order to know this the mid value between this 1 by 8 and 2 by 8. Okay, so 2 by 8 divided by 2 is what I have to have, and that would end up having 3 by 8 and divided by 2. So yeah, so 3 by 16 is the mid value between these 2 points. Yeah, yeah. So now that first of all I need to evaluate the actual height, sorry, actual width minus the ideal step width. So again the ideal step width always is defined by the LSB, and the value of that LSB is nothing but is 1 by 8. Okay, so this is always fixed, which is the ideal step width. Okay, the only thing is that we need to evaluate the step width read from the transfer function. Now in order to read that, I have to measure the width starting from this 1 by 16, sorry, starting from the value of 3 by 16, which is the value that I have here, minus the previous value, which is 1 by 16. Okay, so that is how I measure the width, and due to which this results in 1 by 8 and minus the ideal step width, which is again 1 by 8, it results in a value of DNL that is equal to 0. Okay, so hope that it is clear. So now similarly one can also try to measure the widths in this particular way and then try to get these error values. Okay, so I am not doing it, hope that it is okay. Let me just try it out. Okay, so yeah, so now the next one is to calculate the DNL of 2. Now in order to calculate the DNL of 2, I have to look for this value of 0 1 0, right, and in that I have to measure the width of this particular graph. So clearly you could see that the width is read, the actual width is read by making a note of this value, which is 3 by 8 minus this 3 by 16. Okay. So that is my actual width minus the ideal width, which is always 1 by 8. Okay. So in that case we end up having uh, I guess it is yeah, again a calculation, but what I can see here is that instead of writing in this way, I can just remap these quantities as something like 1.5 LSB, and this one is nothing but just LSB, so or 1 LSB, and due to which the subtraction would give us 0.5 LSB, or in terms of uh, value, this LSB can be multiplied with or replaced with 1 by 8, and due to which we will have a value which is 1 by 16. Okay, so both of these representations are same. Okay, so this is the value of DNL of 2, and similarly let us try to calculate the DNL of 3, and again the way that one could evaluate the value of DNL of 3 is by measuring the width, okay, for the value at 3. So just look for this value of 001 and try to measure the width. Okay, so clearly this width is obviously less than 1 LSB. I guess it is equal to half the value of it, and due to which the total width that I have can be computed by measuring the difference of this value minus this value. Okay, use this color. Yeah. So basically we end up having 7 by 16 minus 3 by 8, that is the actual width, minus the ideal width, which is always 1 by 8. or you can just rewrite this entire quantity that we have here as just 0.5 LSB in terms of LSB, and this also can be returned as just 1 LSB, and you have minus 0.5 LSB, or in terms of value it can be returned as minus 1 by 16. Okay. And similarly one can progress to the other values. So I'll just write down only the end result of this. So DNL of 4 will give us a value of 0, DNL of 5 will give a value of minus 0.5 LSB, and DNL of 6 will give us plus 0.5 LSB. And now I just want to emphasize on this last DNL quantity, okay, so which is DNL of 7, more important. So let me just put a star on it just to ensure that you're pretty clear with this. Okay, so now in this case, first let us try to define the ideal step width. Okay, now what is the ideal step width when we try to have a value of this quantity of 111? Okay, now ideally the value that we have to have as a step width is equal to 1.5 LSB, and this 1.5 LSB happens just because of the offset that we have introduced while while having this quotation error within the limits of plus or minus half LSB. Okay, and due to which we have to have this last value or the last ideal step width to be equal to 1.5 LSB rather than 1 LSB. Okay, so hope that it is clear, and let us try to evaluate the actual step width. So again, by making the difference or making the measurement, um, I guess this line would then intersect here, okay, and this is the maximum value that one could have, and due to which this width is basically equal to 1.5 LSB. Okay, so this particular width is equal to 1.5 LSB, okay, and that value I'll just directly plug in here, which is 1.5 LSB, and due to which the error becomes equal to 0. So ensure that the ideal step width is 1.5, and due to which you are not introducing something like plus 0.5 here. Okay, so hope that you are clear with this. And now one can also draw this. Yeah, okay, so let me just leave that. Yeah, so before let me jump on to the INL or the integral nonlinear error. I just want to talk about two important parameters that are basically associated with this DNL errors. Okay, and those are, let me just write it as two parameters. Uh, they are defined basically with respect to DNL errors. And among this, the first parameter is known as monotonicity, and this is a term that we will be using with respect to the DAC, and there is a second parameter which is known as a missing code, and that is being defined with respect to ADC. Okay. So let me try to define the first one about the monotonicity. And since because it's related to DAC, I'm just putting a DAC across it. Yeah. So now it is something, monotonicity is something like if the DNL of a DAC is less than minus 1 LSB, then the DAC is said to be non-monotonic. Okay. So first of all, what is meant by monotonicity, and why do we call this DAC when it has a DNL which is maybe a value which is, I think it's supposed to be more than this minus 1, minus 2. Yeah. So a DNL which is less than this minus 1 LSB is a DAC if it has such a DNL error, then we call that as a non-monotonic DAC. Okay. So means that the analog output voltage does not increase as the digital input code is incremented. Okay. So this is what we mean by non-monotonic. So let me just demonstrate this particular statement with a kind of graph so that it becomes clear for you. Yeah. So there are two graphs here, and the graph that is towards the left uh, is a normal graph, or a normal transfer function of a DAC, and you could see that there is a DNL error that is introduced at the level of or across the value of 6, which is basically 110. Okay. Yeah. So when this corresponding input is fed in, we are having an output which is rather falling between these 7 by 8 to 6 by 8. Okay. So that is what we have, and due to which there is an error, and the error computation is all what we have discussed in the previous classes, right. Yeah. So we basically have a DNL error which is basically positive, and this is more important. Okay. In that case, uh, you could see that whenever we try to increment uh, the digital input across this DAC, you could see that there is an equal increment at the output as well. Okay. So there is an increment at the output, even when I switch the inputs from 100 to 101, you could see that there is again an increment in the output value, and even when I switch where I have a DNL error at 6, that is at 110, whenever I switch from the previous value of 5, that is 101 to 110, you see still there is an increment in its output value. Okay. So and this happens just because the DNL is basically has a value which is greater than 0. Okay. Even though we have a DNL error at that value of 110, still you could see that the outputs are monotonic, which means that an increment in the input voltage, or an increment in the input digital data, results in incremented output voltage. Okay. So that is what we mean by this. But the figure towards the right, you could see that there is a DNL error across the same input of 110. Okay. So and under that condition, when you try to measure the DNL error, okay, now the measurement of this one results in a negative value of DNL. Okay. And this negative value of DNL will get reflected, as you could see that when you try to switch from a value of 101 to a new value of 110, you see that the output is decremented. Okay. So basically it has to increment, but rather it has got decremented, and the value of this DNL, or just because we have a DNL value which is, when you try to compute, it results in a value which is equal to -1. Okay. And because of this value, probably I should have, yeah, equal or lesser than that. Okay. So whenever you have this value of DNL which is equal to -1, or even further less, like -1.5, in such conditions, we will have an output value which is degraded. Okay. So this is what we mean by this monotonicity, and whenever the DNL, or so whenever the DAC has a value of DNL which is less than or equal to -1 LSB, then the DAC is said to be non-monotonic. Okay. And a DAC should never have this non-monotonicity. Okay. So we have to ensure that the DAC should always exhibit uh, monotonicity, if at all, if it has to function without any error. Okay. So in a way we have to check whether the DNL of your DAC is not falling lesser than this minus 1 or equal to minus 1 LSB. Okay. So, that is what we have to ensure with this thing. So, basically monotonicity is not an error, but it is a kind of property that a DAC has to possess in order to function properly, that is it. Okay. So, let me discuss about this next topic, which is the missing code, and this missing code is basically with respect to ADC, as I stated before. And so, whenever any ADC possesses a DNL of minus 1, then it guarantees to have a missing code. So, let me write this as a statement. ADC having a DNL value which is equal to minus 1 LSB, then it is guaranteed, okay, have a missing code. Now, let me explain this phenomena um, with a kind of transfer function.